Hi, Annie.
Hi, Janakiraman.
Yeah, so in the last couple of weeks, we have actually taken students through, the analog to digital compute domain, and then we also introduced them to a digital computer, right? We also spoke about what a bit is and how data can be represented as bits, right?
Yes.
So I thought now it may be a good idea to just take the students through an end-to-end compute chain, right?
Okay.
So
Okay.
we are used to analog computing, and suppose we were to do some computing in the digital domain in between, right? Then how would that chain look like?
Okay.
And is it the same? Are they equivalent?
Sure.
Right? And advantages, disadvantages. So let's just start with something that we already know. Okay.
And are you going to convert it back to analog at the end?
Yes, eventually I want to convert it back to analog, and then we can drive something. So let's start with our analog mixer that we spoke about. Okay. So plus minus V1. I'm saying now I don't care about these resistor values. It's just an illustrative example. V2. So both are R, which means we know that if I don't have another load resistor, this V out is going to be V1 plus V2 by 2.
Yes.
Okay. So let us take some concrete example. Let's say V1 is 471 millivolt and V2 is 390 or 3, I'll keep it somewhere in between, 43 millivolt.
Okay.
Okay.
Yeah.
So V out should now be 471 plus 343 by 2.
Yes.
Right. And what does this give us? It gives us 814 by 2, 407 millivolt.
Yes.
Right. This is the analog compute answer that we want, and clearly this circuit looks very simple, right? So if I were to do some, if this V1 was coming from some mic, V2 from another mic, I could just feed this out to a speaker, right? And it should drive something. Okay. So this seems a pretty simple thing, but now what I want to do is I want to look at if I were to put in a digital computer in this chain.
Okay.
How would it first of all look like? Okay.
Okay.
So let us first, I'll just take this exact circuit that we have. Okay. And V1, V2, R. Okay. And I'm still doing the compute, the addition in the analog domain for now. Okay. And what I'm going to do is I'm going to put an 8-bit ADC here. Okay, we know what an ADC is.
Yes.
It basically takes an analog voltage, gives you some integer mapping to that number. We can also represent them as bits.
Yeah.
So we'll call this an 8-bit ADC. ADC. So I have 8 bits available here as my answer. 4. Okay. So now if I want to store this data and maybe like we did in Audacity, we have the wave file, store it in the computer and maybe play it back at a later point in time. That's the only thing that I'm trying to do right now. So I have a digital computer here. Okay. Right. And if I want to then get this data out, 4, 5, 6, 7, 8, another 8 bits, I give it to
the 8-bit DAC.
DAC, the opposite of an analog to digital converter, right?
Makes a lot of sense.
Right? DAC, digital to analog converter, and maybe this I can drive to a speaker or whatever. So if you look at the picture earlier, the V out went directly. Okay. Now V out is actually going through something quite complex here in this box.
Yes.
Right? And this is my V out.
Yes.
Right?
Yes.
So there is lot of complexity in this place, but obviously as we saw earlier, this allows you to store this data, right? Earlier there was no way we could do it. We could just do it in real time, but if I had to store it, I had to do this. Now we could alternately do another thing, right? Let's say I want to move my entire compute, right? Now the computer is only being used to store data.
That's right.
Let's say I want to move my entire compute.
Oh, even the mixer into.
Yes.
Oh, I see.
Into digital. I could do that, right? So if I were to look at that, I again take a digital computer here, okay, digital computer, and let us say it has, like we saw in that motherboard, right? There was 3, 4, 6, 7, 8, okay, ADC, and this accepts either V1 or V2, okay. So I will just use, since we have already introduced students to switches, I will use the concept of a switch here, okay. This is switch S1, plus minus V2, V1 and S2.
You now no longer require those resistors for mixing.
Exactly. That circuit is gone now, right? So if I were to then do this, right? So 1, 2, 3, 4, 5, 6, 7, 8, 8-bit again DAC, right? And I am going to feed this to V out. Okay, now this is slightly more interesting because when I turn on S1 and keep S2 closed, V1 will appear at the ADC.
If you keep S2 open, you mean?
Yes, S2 open, I'm sorry. S2 open, S1 closed, right? V1 is going to appear at the ADC.
That's true.
You digitize that and you can store that in the digital computer, in the memory, right? We saw what that memory was, right? And then, so let's say there is a memory here, okay?
Yes.
In one location, okay, I'll use red for V1, okay? I'm going to call this V1 and I'm going to use magenta for V2. So in an other location, I store V2 like this.
Perfect.
So all I have to do is time the switches so that one voltage at a time appears. That data can be stored in the thing. So now I have the data stored. I can do anything I want with this data, right? It's not necessary I should do only addition. I can do multiplication, whatever I want.
Filtering,
right?
For example.
Filtering, exactly.
Yeah.
So now let's say I wanted to replace exactly this addition operation, right? We wanted to do V1 plus V2 by 2.
So interestingly, now I noticed something. You are basically storing V1 and V2 separately.
Yeah.
You can do the addition and store that as well.
Exactly.
Right, and replay it. You can do all kinds of things now that you have storage.
Exactly.
Right?
Exactly.
Whereas originally in your analog mixer,
yes,
you are constrained by the fact that you get a continuous waveform of V1 plus V2.
Yes.
And once you have mixed them, separating them out is difficult.
Is difficult.
Right?
Exactly. Right?
Okay.
And in this case also, in the first case here, I only have the sum V1 plus V2 by 2, which I have stored, right?
Separating them is not
I cannot get V1 and V2 out separately. Exactly. Right? So anyway, so I have this
because that
data.
I can imagine that giving you a lot of flexibility. You can filter out only V1 and not V2. And then mix them.
Exactly.
You can do all kinds of things.
You can do all sorts of things, right? So in fact, in Audacity, if I had V1 as a separate track, V2 as I could do equalization on one.
Yes.
Different equalization on V2 and then mix them. Right? That's the advantage.
That's the power of doing digital
computing. Right? Exactly. Right. So, but what we will now do is we'll go through the specific examples that we took. Right. We took V1 equal to 471, 343. Right. So we said this is, let me write that down, 471 and V2 is 343 millivolt.
Yeah.
Millivolt. Okay, I'm going to keep this color convention the same all through, right?
Sure.
So please correct me if I mess up on that.
Sure.
Right? Okay, so what we are going to do now is, we saw that the resultant answer was 407 millivolt.
Correct.
Okay. Now, let's assume that I have an ADC, 8-bit ADC, and the range that the range of voltage that it can digitize is 0 to 800 millivolt.
Okay.
So that it's very simple, right? And I've been saying 8-bit ADC. I think let's simplify that to maybe 3 bits.
3-bit ADC.
Yeah, okay, yeah. So let us now simplify the
So 8 level ADC.
Exactly, 8 level ADC, right? What I'm showing here is a more practical case. You have an 8-bit ADC. For illustration, I'm going to deal with an 8 level ADC, which means this is effectively 3-bit.
Yes.
Okay. So what does that mean? It means that you take, this is my input, okay, V in, I get 3 bits out of this, which will represent one of 8 levels, okay. And what are the 8 levels? So if you look at this, I am talking about the, so let us say these are binary bits B0, B1, B2, okay, and together P2 is the MSB, B1 is the next bit and B0 is the LSB. It represents a number n. Okay, so what I am plotting here is that n versus V in, right. So I have only 8 levels and let us say this guy here is 800 millivolt. So I am going to divide this 800 millivolt into 8 levels, right. So effectively I will get, this is 400 millivolt, 200 millivolt, oh sorry, 600, yeah, 600. 200, right, and then I have the half further 100 millivolt.
Right. So do you want to make the lines vertical? So the voltage axis on the x-axis, right? Do you want to plot it that way? Do you want to plot, so this n is also in volts?
N is also in volts. N is effectively, is a number.
Right? Which means these lines should be vertical.
Right.
Or you can, why don't you plot V in versus N if that makes it easier
I think
for
that's
you?
okay. V in versus N.
Yeah.
Right? Okay. So then I have, you're right. Thank you. Yeah. So I have,
maybe the only thing is student may be confused because input is Vn. Yeah. We're plotting that on the y-axis.
Okay, so we'll do that. We'll do that then. I think you're right. Let's just
maybe a little bit.
Keep it. Yeah, exactly. Okay. So I want to do V in N versus V in. Correct. Right. So effectively, what we want is.
So these will be numbers 0, 1, 2, 3.
Exactly. So these are numbers saying 0, 1, 2, 3, 4, 5, 6, 7.
Yes.
Okay. And on the y-axis, as you said, on the x-axis, I am going to have this 0 to 100 millivolt.
Yes.
So if any input is between 0 and 100 millivolt, it will come out as code 0.
Code 0.
Correct. Right? And then, so you're right. So let me put that 800 millivolt here. This is 400, 600, 200.
Yes.
Yeah. And this is 100, 300, 500 and 700 millivolt.
Perfect.
Right? Everything. So this is going to be in millivolt. So if the input is between 0 and 100 millivolt, you get code 0.
Correct.
Between 100 and 200, you get 1.
Yes.
Then between 200 and 300, you get 2. Then like this, you go all the way.
Perfect.
Right?
Yes.
Right? And eventually you get, it will all get rounded off to
700
millivolt.
7 is the largest number.
Is the largest number, exactly. Okay, so therefore we are going to say that you will get a code of 7 for anything between 700 and 800 millivolt. Beyond that, the ADC does not accept as a valid input, right? Okay, so now what we have is, we have two things, right? We have two input voltages, 471 millivolt and 343 millivolt.
Yes.
Okay. So what is this? We have 471 millivolt, which is somewhere here, right? This is my V1, 471 millivolt,
Yes.
right? And then the magenta is 343, somewhere here,
Yes.
V2, 343 millivolt, right?
Yes.
So therefore, the code corresponding to V1 in
Yes.
red
Yes.
is going to be 4,
correct.
right?
Correct.
Now the code corresponding to V2,
1 minute. So V1 is 471, so
yes,
it will be 4.
4,
Correct.
and the code corresponding to V2
Yes.
is going to be 3.
3.
Okay.
That's right.
So now what we want to do is, we are looking at, there is an other voltage, right, which has come out, which is the analog compute voltage,
Correct.
which is 407 millivolt,
Correct.
and I'll use a different color to represent this,
Yes.
7 millivolt.
Okay.
Okay, and where is that? Now that is sitting very close here to this 400.
Yes.
Okay, so this is here, this is V out equal to 407 millivolt. So V n out, okay, the ADC value, which value? We are talking about the ADC that comes out of here.
Correct.
If this were a 3-bit number,
Yes. Correct.
okay, that is going to be, still it is going to be 4,
Yes.
right?
Correct.
So effectively, so now what we want to do is, we want to go back and see if I took this number, right,
Yes.
put it into a computer like this,
Correct.
right, which means this 471 millivolt now corresponds to a number 4.
Yes.
This 343 millivolt corresponds to a number 3.
Yes.
Okay. So now what am I going to do? I am going to go ahead and compute this number digitally,
Yes.
right?
Correct.
Digitally. So what is this number now?
So you are now going to do N1 plus N2 by 2
yes,
by chance?
I am going to do N1 plus N2. So this one, if you look at in the digital domain, in a 3-bit representation, it is this, because 2 power 0, 2 power 1, 2 power 2.
Correct.
Right? And this guy corresponds to a number 0, 1, 1.
Correct.
Okay. So now what I am going to do is, I am going to add these two numbers.
Yes.
Okay. And then I am going to divide by 2. So you get the sum, and this is again, I'll use a different color because it's now being computed digitally.
Yes.
Right. So this will give me 7, right,
which is 111.
111 by 2. I have to do this.
Yes.
Okay. So, and what is this answer therefore? If I get 7 by 2, approximately it will be
So 3.5.
3.5. Again, it depends on how we deal with the
Correct.
fractions,
Fractions,
right? So we could deal with this as,
So maybe we'll just round it up.
we can round it up, right?
Right.
It could be 0, 1, 1.
Yes.
It
So
could
that
be
now you
3.
have rounded down.
I have rounded down,
Okay,
right?
okay.
Otherwise, you could round up, it would be 100.
Correct. Because of the quantization, you have to round up or round down.
Round down, right?
Right.
So you could have, the whole point is in this digital computation, there will be this quantization error.
Correct.
Right?
That,
That
last bit can change by 1 or
Exactly,
one,
exactly.
one value.
One value, right? So effectively, what we have here is the answer when computed digitally, right, through the digital addition
Yes.
was going to be 011 or 100, depending on how you choose to deal with that number.
Correct.
Right? And on the other hand, what we got from the analog computed value going through the ADC, we got that to be 4.
4. Correct.
Right? So
Correct.
this number was 100.
Yes.
Okay.
Correct.
So, and the, so maybe I'll just write that down. This is the ADC value of,
V1 plus V2 by
yeah, exactly. I'll just say that. V1 plus V2 by 2.
Yes.
Okay. And on the other hand, I have an other D out, the digital out,
Yes.
okay, as either 0, 1, 1 or 1, 0, 0, depending on whether we choose to round up or round down,
Correct.
right?
Correct.
So that's okay. So this is the digital output, right? If we get.